In chapter 20, we started looking at magnetic fields, and we saw that when you induce a current in a wire, that current produces a magnetic field around the wire. So that begs the question, can we induce a current with a magnetic field? Basically flip that around. A current induces a magnetic field. Can you get a magnetic field to induce a current? And that is the subject of this chapter, chapter 21, on electromagnetic induction. And in this video, we'll talk about the beginnings of this electromagnetic induction and about Faraday's law. Now, Michael Faraday, was a young scientist about 200 years ago who looked for evidence that magnetic fields could induce an electric current. He had some sort of an apparatus like this, where he had a coil of wire around a piece of iron connected to a battery with a switch. And then he had another coil, which is also connected to the piece of iron, which is then connected to some sort of measuring device. We'll call it a galvanometer in this figure, but it could have been anything. So the question was, could he find a way, could he create a current by inducing a magnetic field? Well, the short answer is yes, he could. He found no evidence that when the current in the left-hand loop was steady, so if he closed the switch and then left it alone, just let that current flow, nothing would happen. But he did notice that as he closed the switch, the galvanometer would flip a little bit. Then as he opened the switch again, the galvanometer would flip the other way really quickly. So he did see that a current was induced in the right-hand loop when the switch was turned on or off. Let's look at another simple experiment that kind of helps us to see a little bit better what's going on. If you have a loop of wire, and then you hold a magnet close to that, and then start to move the magnet in one direction, that's going to induce a current flowing in a particular direction through that loop. If you pull the magnet the other direction, then it induces a current going the other direction through that loop. And yet, just like Michael Faraday saw, if you just hold the magnet there and have no movement at all in the magnet, then there is no current at all in the loop. So what we see then is that a current will be induced in a wire loop if a magnet is moved through the loop, but not when the magnet is held steady. Therefore, we see that a changing magnetic field induces an EMF. In summary, we saw in the first experiment, Faraday's experiment, he used a magnetic field he saw a magnetic field that was changing because of a current. So he produced a current that generated a magnetic field. And that changing magnetic field induced a current, or an EMF, in the second coil. Whereas in the previous slide, we showed a straight up magnetic field from a magnet that changed the magnetic field, that induced an EMF because the magnet was moving. Okay, so let's look mathematically at how this changing magnetic field induces an EMF. So the induced EMF in a wire loop is proportional to the rate of change of magnetic flux through the loop. Remember back in chapter 16, we talked about electric flux, how much electric field was passing through an area A. Well, magnetic flux is very similar. We take the magnetic flux to be the component of the magnetic field that is perpendicular to a surface A times the surface area A times the cosine of the angle between them. So that would be this angle theta right here. Okay, and this is how you calculate magnetic flux. The units of magnetic flux are known as a Weber. So 1 Weber would be the product of 1 Tesla times 1 square meter. So the magnetic flux is analogous to the electric flux. Remember that the electric flux was the electric field times the area times the cosine of theta, which I've rewritten for you here. Whereas the magnetic flux is the magnetic field times the area times the cosine of theta. It's the exact same equation. But that begs the question, where is this angle theta measured from? Remember that to do this with the electric field, we had to take the surface of our object, whatever it is, and draw a line perpendicular to the area, and that's the vector that describes the area A. So in this left-hand example where I have the area vector, it's going upwards, the magnetic field's to the right, therefore they're at 90 degrees. Cosine of 90 degrees is 0, therefore there is no magnetic flux, meaning that there's no magnetic field passing through the area A, which makes sense here. In the second figure, my vector A would be moving down and to the right at a 45-degree angle to the magnetic flux B. And so the magnetic flux, 45 degrees to the magnetic field B. Therefore, the magnetic flux would be BA cosine of 45 degrees. And in the right-hand figure, your loop is vertical, which means your area vector is horizontal, which means it's parallel to the magnetic field B, angle of 0 degrees. So the magnetic flux would just be magnetic field times the area A. Okay, so that's magnetic flux. But we said in the previous slide that the induced EMF is going to be proportional to not the magnetic flux, but the change in magnetic flux. So as it stands right here, the magnetic field passing through a loop of wire, it's not going to do anything. But if you somehow change that magnetic flux by either changing the magnetic field or the area or the angle, then you can induce a change in magnetic flux, and that will induce an EMF in the coil of wire. Here is Michael Faraday's law of induction for one loop of wire. The EMF that is induced in a coil of wire is going to equal the negative change in magnetic flux divided by the time it takes for the change to take place. That's if you have one single loop of wire. But what if you double it over until you have 2 loops? What if you have 3 loops? Well, it turns out that this is the EMF induced in each of the wires. So if you add them all together, then for n loops, it'll just be n times that. So the induced EMF would equal negative n, where n is the number of loops of wire, times the change in magnetic flux divided by the change in time. Okay, so the change in magnetic flux, we talked about that. Change in magnetic flux over change in time, that's the rate of change in magnetic flux. N is the number of loops of wire. Great. What's this minus sign? Where did this minus sign come from? Well, this minus sign comes from something called Lenz's law. And it gives us the direction of the induced EMF. A current produced by an induced EMF moves in a direction so that the magnetic field produced by that current restores the changed field. In other words, if you have a magnetic flux that decreases, the induced current will be in a proper direction to resist that change and increase that magnetic flux a little bit. If you have a magnetic flux that's increasing, then the current will be in a direction that opposes that change. It'll then decrease. Let me show you a quick example here. So you have in the left figure, well, remember I said that the change in magnetic flux can happen by either changes in the magnetic field, change in area, or change in angle. We're going to look at all 3 of those. First of all, we're going to look at the change in the magnetic field itself. So we've got magnet passing through a wire. the magnetic field is increasing, and so this is going to produce it's going to induce a current with a magnetic field that opposes the increase. So let me see if I can draw this well enough here. Since the magnetic field is increasing, it's going to produce a magnetic field that opposes that. So that's the induced magnetic field. What direction does the current need to flow in order to create that magnetic field? It has to flow this direction. You can use the first right-hand rule to find that. Point your thumb in the direction of the magnetic field. Your fingers will wrap in the direction of the current. And you'll see that the figure has put the current in that proper direction. Now look at figure B. In figure B, the magnet is moving down, so the magnetic field is weakening. Well, the induced current is going to fight that weakening magnetic field, so it's going to create a magnetic field that actually strengthens the magnetic field in the center. And again, if you follow the right-hand rule, point your thumb in the direction of the magnetic field, your fingers will wrap around in this direction. And so that would be the direction of your induced current. Okay, so we see that if a magnetic field changes, we have a change in magnetic flux, thus we have an induced current. We can also change the area. Let's say you have a number of loops of wire in a magnetic field, then you pull on the sides of the loop, and by pulling on the sides of the loop, you stretch the wire so that it changes the area of the wire. Well, by changing the area, you change the magnetic flux, and so you're going to induce a current inside of that loop of wire. You can also induce a current by changing the angle. Here you've got that same loop of wire, but instead of changing the area, we're just going to turn it sideways. Here you've got a lot of magnetic flux, but by the time you turn it 90 degrees, magnetic is flowing into the page here, but the area is in this direction. So there's no magnetic field passing through the loop at all, so you have zero flux. You've changed your magnetic flux, therefore you're going to induce a current in that loop. So here's how you solve induced EMF problems with Lenz's law. First of all, you need to determine whether the magnetic flux is increasing, decreasing, or unchanged. And then second, you create a magnetic field due to the induced current that points in the opposite direction of the change. So if the original field of the flux is increasing, then you draw a magnetic field opposite that direction. But if the original magnetic field is decreasing, then you need a magnetic field in the same direction as the original magnetic field to oppose the change. If the flux is not changing, then you're going to have zero change, therefore zero EMF. Then you use the right-hand rule to determine the direction of the current. Point your thumb in the direction of your induced magnetic field. Your right-hand fingers will wrap in the direction of the induced current. And then you have to remember that the external field and the field due to the induced current are different. The external field is whatever you had to start with, and the field due to the induced current is the magnetic field that's produced because of the change. So a couple of very important points there to remember. But follow these points. They really help with solving for the direction of induced EMFs, induced currents during an induced EMF.